All right, so here we have another series, and it looks like the nth term is given here. So again, I'm going to apply the ratio test to it. But in this case, I want to find the interval of convergence. So this is going to be a little bit more work. All right, so the nth term, it looks like an alternating series, but that's okay. We can still use the ratio test on the alternating series. So I'm going to write the ratio of the n plus 1th term over the nth term, and that's going to be equal to minus 1 to the n times x minus 1 to the n plus 1 over n plus 1 times 3 to the n plus 1. Okay, so that's the n plus 1th term, and then I want to multiply that times the reciprocal of the nth term. So that's going to be n 3 to the n over minus 1 to the n minus 1 times x minus 1 to the n. Okay, absolute value of that whole thing. All right, so I don't really have to worry about these minus 1s since I'm taking the absolute value of it. And then I can simplify this. If I divide x minus 1 to the n plus 1 divided by x minus 1 to the n, I just end up with x minus 1. And I can also cancel this. So this 3 to the n plus 1 divided by 3 to the n is just 3. So I get a 3 in the denominator. And so now let's see what we have left. So I have an x minus 1, and then in the numerator it looks like all I have left is n, and in the denominator I've got 3 times n plus 1. 3 times n plus 1. Okay. All right, so now let's take the limit as n goes to infinity of this thing, x minus 1, n over 3, n plus 1. All right, so the n over n plus 1 part just goes to 1, but we still have this 3 in the denominator. So it looks like it's going to be 1/3 x minus 1 is what the limit goes to. And in order to converge, I want this to be less than 1. So let's multiply both sides by 3. So I get x minus 1 is less than 3. Okay, so this is the radius of convergence. All right, so here we have one that's not 1. Convergence. All right, so that's the radius of convergence. But now if we want the interval of convergence, we just have to test the endpoints. So let's find out what the endpoints are. If we rewrite this as x minus 1 is between 3 and minus 3, then if I add 1 to everything, then I get x is between minus 2 and 4. Okay, so that's our interval, and all we need to do is test the endpoints. So let's first of all start with x equals minus 2. All right, when I plug that in, I just got to plug that into the original sequence. So n equals 1 to infinity of, so let's write this out, minus 1 to the n minus 1, and then we have minus 2 minus 1, so minus 3 to the n over n times 3 to the n. All right, so what is that? Let's simplify that a little bit. So we have the summation n equals 1 to infinity. So let's think about what's going on here in the numerator. You can see that minus 1 is to the n minus 1, right? And minus 3 is to the n. Okay, so when n is even, this minus 3 to the n is going to be positive. but the minus 1 to the n minus 1 is going to be negative. Okay? If n is odd, then the minus 3 to the n is negative, right? But then this n minus 1 is even, so then minus 1 to the n minus 1 is positive. So what we're going to end up with is something that's always negative in the numerator, right? So we have a negative, and then we have this 3 to the n. 3 to the n. Okay? Does that make sense? Hopefully that makes sense. Because of the fact that these exponents are 1 away from each other, one of them's going to be even, one of them's going to be odd. And so you're going to have a positive times a negative or a negative times a positive, depending on whether n is even or odd. But either way, it's going to end up being negative. Okay, so that simplifies the numerator. And then we have n 3 to the n. Okay, so that allows us to cancel the 3 to the n. And so what we end up with is the summation n equals 1 to infinity of basically minus 1 to the n, which is a constant multiple of the harmonic series. It's a minus 1 times in the harmonic series. So, so we know it diverges because the harmonic series diverges. All right, so we're not going to include minus 2 in our interval of convergence. All right, so now let's test the x is equal to 4. So if we plug that into our series, n equals 1 to infinity of, so we have minus 1 to the n minus 1, and then we have 3 to the n, right, because 4 minus 1 is 3, over n 3 to the n. All right, this one's a little simpler. It's obviously this 3 to the n will cancel, and then we end up with the alternating series, minus 1 to the n minus 1 all over n, which we know converges, right? It's an alternating, it's a harmonic series, but it's alternating, so it converges. Okay. So we want to include 4 in our interval. So let's write down what the interval of convergence is. Interval of convergence. Okay, so we're going to, we are not going to include the minus 2, but we are going to include the 4. Okay, so that's one way to write the interval of convergence, or we could write minus 2 comma 4 with a square bracket around the 4, indicating that that point is included in our interval. All right, so that takes care of all the examples. Now, in the discussion questions, there are examples of some special cases that I didn't talk about in these examples. And those special cases are back here in this box. Cases where we run into the a radius of 0. So we have a 0 interval of convergence. So essentially it only converges when x equals a. Or we have a case where the radius of convergence is infinite. Okay, but I think that'll make more sense when you actually go through the examples. So you'll see it emerge. There's an example of each of these in the discussion questions. So I will see you in class.